Greetings all. So up till now we have studied about the critical thickness of insulation for cylinder and sphere, and we have also derived the relation for them. So this is the critical radius of insulation for sphere, and for cylinder it was H naught K insulation by H naught for cylinder. So this was for cylinder and this was for sphere. So we can see radius is twice, critical radius is twice in case of sphere as compared to the cylinder critical radius. So now we will dive more deeper into it. So also we have looked at the purpose of the electric wire is to provide safety, and we insulate them to provide safety from electric shock. That is the first reason from the electrical point of view, and from the thermal engineering point of view we insulate them to increase the heat loss. Okay, so in case of electric wire, always remember that we need that heat loss, higher the heat loss for in case of electric wire, higher will be the current carrying capacity of it. Okay, so higher the heat loss, higher will be the current carrying capacity of the electric wire. So we insulate them so that heat loss increases and they can carry more current in them. Okay, from the power supply. So when we insulate the electric wire, our objective is that after insulation the heat loss must increase from the wire, right, and its current carrying capacity increases. I hope you understood it. And in case of steam pipe which is carrying steam in the power plant, our objective that steam should not condense and it should reach at the proper saturated or super saturated state to the turbine, and it should produce power. For that we want that steam which is carrying by the long pipes in the power plant, they are insulated from outside surface so that steam don't condense and no vapor should form inside the pipe. And okay, because if vapor forms then it can deteriorate the turbine blade. So objective in case of steam pipe is that when we are insulating them, so after insulation the heat loss must decrease. Okay, then their heat loss, their objective is different, and in case of electric wire objective is different. So after that we must look at that what is happening and why, what is the mechanism, and what are the insights of increasing the heat loss or reducing the heat loss in case of critical thickness concept. So if we plot the conduction and convection resistance, so as we saw previously, so let's say this is the material, let's say it is a cylinder and we are insulating it from the outside. This is the insulation. Okay, so this is the radius r1 and this is the radius r2. Okay, of the insulation, r1 is the base material radius. Okay, or it is also called the radius of the bare material, right? So when we insulate it, so conduction resistance of the insulation will come into picture. All right, so as we, and for total resistance we can write that the conduction resistance from this material of insulation and the convection resistance from the outside. Okay, so for cylinder, let's say we are writing like conduction resistance as this, convection resistance as this. R is the radius of the insulation, right? Radius of the insulation at any r, we can change that, this radius can change, right? So if we increase the radius r, and let's say we are at radius r1, then our conduction resistance will be 0. It means that there is no insulation, but there is no insulation, and if there is no insulation, there is no conduction resistance due to insulation. So that's why conduction resistance graph start from origin, and it will increase when we increase the radius of insulation, because it is from intuition we can say that when we are putting the material, there is extra cost of that insulation which is coming in because of the conduction resistance. So conduction resistance will increase when we increase the material. Okay, and similarly convection resistance, when we are not insulating the material. Okay, when the let's say cylinder was bare, there was no insulation, then the radius was only r1. Okay, as we can see. So but when we start insulating it, the convection resistance is like this: h times 1 by h times 2 pi rl. So as we increase the r, that is the radius of the insulation, as we keep on increase the r, that ratio will decrease. It means convection resistance will decrease. That's why this red color graph is going down, and it is starting from some value. Okay, if we plot this resistance, we can see that there is some minima point is occurring of the total resistance, and this minima point generally occur at the critical radius of insulation for the case of cylinder as well as sphere. Similar argument we can put for sphere, which we have put here: critical radius. So similar argument we can put for the sphere also, which we have put to explain this resistance versus radius or thickness curve. Okay, so total resistance is minimum. So when total resistance is minimum, heat loss will be maximum. How we are saying that? Because heat loss is delta T divided by total resistance. So if total resistance is minimum, and when it is minimum, total resistance is minimum. So we saw from here that from the last lecture that the double derivative of the total resistance was positive. It means total resistance is minimum at critical radius, and this is dictated in the graph here also, right? This graph also dictating the same phenomena. Okay, so if total resistance is minimum, heat loss will be maximum, and which is depicted by this graph. Okay, I hope you understand it. So always remember that RC is the radius at which total resistance is minimum and heat loss is maximum. So let me put that in point. RC is the point, RC is the radius, at which heat loss is maximum and total thermal resistance is minimum. All right. So next thing is, suppose let's do some thought experiment to understand this phenomena more comprehensively. So let's say we are at this radius r1. R1 is the radius when there is no insulation on the material. Okay, and let's say we at r1, and the radius of the base material is r1, and let's say we have r1 is less than rc. We can know, we can calculate this for cylinder. It is K insulation of the material divided by H naught surrounding heat transfer coefficient, okay, for cylinder. So we can find for each geometry what is the critical radius, right? So let's say the material that the base material size is less than the critical radius, okay. Then what happened? Then we are here, it means we are here if our radius is less than critical radius, right? So if we keep on insulating, what will happen? So if we keep on insulating, first heat loss will increase, keep on increasing until critical radius is reached, okay. So it is like that. On base material we are keep on insulating, but the heat loss is increasing. So we have to reduce the heat loss. Let's say for steam pipe, to reduce the heat loss we have to insulate it more, right? So that heat loss must decrease, okay. So the for the first case, if R1 is less than RC, then due to insulating the material, heat loss first increases up to critical radius and then decreases, okay. Now let's see the flip side. When R1 is greater than RC, let's say we are here, the material size is such that it is more than the critical radius. So when material size is more than the critical radius, if we insulate, heat loss will always decreases, right? So let's say steam pipe size is such that it is more than the critical radius, so if we insulate it, heat loss will decrease. So for wires, the size are generally small, so we have to work in this area for them to increase the heat loss, and for steam pipe we have to be in this area for reducing the heat loss, okay. So for second case, due to insulation, heat loss always decreases, and the condition for maximum heat loss is what? At critical radius, at R is equal to RC, heat loss is maximum. That is the condition. So this is all for critical thickness of insulation. So in the next part we will see about the variable thermal conductivity concept and heat generation concept in conduction. Thank you.